Hello and welcome back to OTS. In this video, we'll be going over something known as static equilibrium. Static means it's not changing, right? Or in other words, if you remember F static, it's not moving. Equilibrium means it's in balance. So it's probably maintaining this state. Okay, it's not just like it happens once and then it's leaving. Equilibrium means it's in balance and it's continuing to maintain the state. Okay, so let's look into what this could look like, because there's many examples, which we'll be covering in torque as well. But regarding force, there's a few examples in specific you need to wrap your mind around. Okay, so net force in the x direction has to be equal to 0, and net force in the y direction has to be equal to 0. That makes a lot of sense, right? If you have any force, so even if you have a tiny force in the x direction, that is still force. Okay, you're going to move because force is going to cause objects to move, push or pull. But if you have same thing regarding the y, right? If you have any force in the y direction, the object is going to move in the y direction, either up or down, doesn't matter, but it's going to move. So in order for there to be static equilibrium, which means the object is not moving because it's in equilibrium, both the net force x has to be 0 and the net force y has to be 0. Okay? And it makes sense why both must be true, right? If either one was not true, and that means the object would be moving in that direction, which we don't want. Static equilibrium means both of them are not moving. Both forces, net forces, are 0. There could be forces, but the net force has to make 0. So the forces could cancel each other out. So let me give you an example of what a problem like this regarding static equilibrium could look like. Okay? Imagine you have a rope, okay? One rope at 40 degrees, like this, 40 degrees below the horizontal, attached to a 40 kg block. And one rope at 65 degrees below the horizontal, attached to the same 40 kg block. Okay? And mg here is 392 newtons. Okay, so they gave us that. You could have calculated it, right? 40 times 9.8. But they gave it to us, so we can chillax in that sector. And they ask us to find both the forces of tension here. That's interesting. And they told us one more condition. They said the block is in static equilibrium. Okay? Which means it's not moving. If you recall the two conditions for that, net force x has to be equal to 0, and net force y has to be equal to 0. Okay? How can net force x be equal to 0? That means these two has to cancel each other out, okay? These two forces here. So this force, tension 1, is trying to pull the block in this direction. This force, tension 2, is trying to pull the block in this direction. So the x forces for both of these should cancel out. Now let me show you how that will look like. For the x forces, you want to look at only the x components, right? So let's break this down into components. Tension 1, okay, cosine 40, and then tension 2, cosine 65. Could you think of what the relationship between these two should be? They should be equal, right? Because only then, when you subtract them from each other, you're going to end up with 0, because they'll be acting in opposite directions, and then you're going to end up with 0, right? So, sorry about that. So, you understand that tension 1 cosine 40 minus tension 2 cosine 65 is equal to 0, right? This could be tension 2 cosine 65 minus tension 1. I'm just saying they're in different directions, and they're basically equal to each other. So the one subtracting the other should be equal to 0. And then what about the signs? How do we find out the vertical components? So this is net force X, okay? We know this has to be 0, that's why these two are 0. Otherwise, the object would be moving in that direction because of one of these ropes. So for the y direction, same thing. We're going to break them down into components, okay? So we're going to break tension 1 into sine 40 degrees. We're going to break tension 2 into sine 65 degrees. Okay? And they're both pointing in the same direction, right? They're both pointing upward. The rope is hanging on this, so both of them are going to be pointing upward. And guess what? This force has to sustain what? mg, right? Because if this force was greater than mg, the block would be pulling up. If this force was lesser than mg, the block would rip through the ropes and it would fall down. In order for the block to be stationary over there, the y components of these two vectors, t1 and t2, should match up to the mg and cancel it out. Which means tension 1, sine 40 degrees, tension 2 plus tension 2, sine 65 degrees, has to equal mg, which is 392 newtons. Because these two are pulling in the upward direction, you add these two, and then you cancel out with the downward direction mg. And if you get 0, that means you're in static equilibrium, right? Since we know we're in static equilibrium, I can say this. Because otherwise, then we wouldn't know, right? But we know that these two have to exactly match up. Then net force y is 0. They cancel each other out. The upwards y direction of the ropes cancel out with the mg. Okay? So this is all right. This is what we good. Now, how do I find either tension? Well, good question, right? It's a tad bit complicated, but not conceptually, but the algebra can get a bit messy, okay? So make sure to stick with me. T1 cosine 40 is equal to T2 cosine 65, right? Because they have to be equal to cancel each other out. Otherwise, you'll be moving in the x direction. So T2 is equal to T1 cosine 40 over cosine 65, right? Okay, that's pretty intuitive, I'd say. And then what is about this? How can we simplify this a bit more? So I'm going to bring this over here. T2 is equal to, we can divide cosine 40 divided by cosine 65, right? And then we can get a ratio to multiply to T1. So let me go and do that. Cosine 40 divided by cosine 65. Okay, that's 1.8. 1.81 and times T1, right? So T2 is greater than T1. All right, that's fine. Now, what can we do with this knowledge? We can substitute this value in to the sine equations, okay? So basically substitution, just the same thing as substitution, right? Basically elimination would be a tad bit more complicated because all these signs, you'd have to multiply them out, lots of decimals, lots of gibberish. So we can just substitute them in. So T2 is equal to 1.81 T1. So when I see T2 in the sine equation, I'm going to replace it with T1 sine 40 degrees plus 1.81 times T1 times sine 65 degrees is equal to 392 newtons. Okay, so this should be equal to, so multiply, what is sine 40? Sine 40 is 0.6, so 0.64 T1 plus 1.81 times sine 65. So that's going to be the header for this T2, T1. 1.64 T1 is equal to 392 newtons. Now what I did here is a bit dangerous, okay? I just did it to show you out loud, but I would usually just add them together, okay, by the decimal point. I wouldn't round them like I did here. The rounding would come in the later steps. So I'm just gonna keep the answer in my calculator. I'm not gonna write it out all out, but you can see how I did that. So this gives me around 2.28 T1 is equal to 392 newtons. Okay, so T1 is equal to 392 divided by 2.28. It's equal to 392 divided by 2.28. 171.93 newtons. And you see how, so if I erase this so you can see a bit, you see how over here I got 171.50. That's why I shouldn't have rounded, okay? I was just rounding to show you guys, but generally I would not recommend rounding. You see how they're all to like the fourth digit and all that here? I would just keep that in my calculator and use those by pressing second and answer, okay? And using those for like the full digits. So I would not recommend doing what I did. All right? And then I was just doing it to show you. Okay, I wouldn't do that on a test. T2 is equal to 1.81 times T1, right? So T1 is this, 171.93. So T2 should be 1.81 times 171.93. Again, I wouldn't have rounded it to 93, but I would have probably kept it at 171.929 because it's not the final answer, right? T2 is equal to 311.19 newtons. Okay, so yeah, slight differing answers here because I rounded it too much. That was just to show you guys though, okay? I wouldn't do that. And I wouldn't advise it either. Yeah, so that's how you'd walk through static equilibrium, okay? That's how you find tensions in ropes given just the mass of the object and how gravity is pulling it down. And we know that these two ropes have to match that, okay? The vertical components have to match gravity and the horizontal components have to cancel each other out. And then you can have a system of equations to use. So yeah, let's try some practice, okay? A 30 kg flower pot hangs from two ropes at 50 degrees and 70 degrees from the ceiling. Find both rope tensions. Okay. So since this is 30 kgs, mg is going to be 30 times 9.81 or 9.8, which is just 294 newtons. Okay. And so again, that was a bit, be partial to my system right now. That was a bit, it was just glitching a bit. Okay. So then we know that the cosine and cosine values here have to match up because the block is not going to move in the x direction. So T1 cosine 50 is equal to T2 cosine 70. Okay. And the sines, T1 sine, so both of these are going to contribute here, upward, but they have to match mg, otherwise the block would be moving upward, right? They're going to just match it. T1 sine 50 plus T2 sine 70 is equal to 294 newtons. Okay, those are my two equations. So over here, I could just do T2 is equal to T1 times cosine of 50 over cosine of 70. So otherwise, 1.8794. 1.8794 T1. Okay? And then obviously I still wouldn't recommend rounding, even though I went way more precise this time. But this is just to show you. And then I could plug this in to this, right? T1 sine 50 plus T2 is 1.8794 T1. So times T1 times 70 sine of 70, is equal to 294 newtons. So sine of 70 times 1.8794, okay, times 1.8794. And then that plus sine of 50, because that's this header, right? So I'm getting around 2.5321 T1 is equal to 294 newtons. So T1 is equal to, let me scroll up so you can see a bit, 294 divided by 2.5321. In other words, 116.11 newtons. Okay? And I can use this. So T2 is equal to 1.8794 times T1. So 1.8794 multiplied by this business, 116.11. So T2 is around that 116.11 times 1.8794, or 218.22 newtons. Okay, and that's how you find tension using static equilibrium. Pretty neat, right? So that's it for that problem. Now we know we have a 150 newton. So always remember, right? If this is the weight, so we already know mg here. We don't need to calculate mg using the kgs, because if it's in newtons, that means it's the weight. Each 25 degrees above the horizontal on either side. Find each cable's tension. Okay, so basically cosine 25. So the cosines already match up, right? Because they're just, I don't even need to write an equation for that, because I know both these tensions are going to be equal because they're both 25 degrees above. And they're both the same length, right? Same length of cable. So this is going to be the same. And then the only way I can find this is using the y components. So t sine 25 plus t sine 25 is equal to 150 newtons, right? So this is 2t sine 25 is equal to 150 newtons. T is equal to 150 divided by 2, 75 newtons, divided by sine of 25 is equal to around 117.465, or I could just round it up to 47 newtons. And this is going to be for both of them, right? Because they're both identical. So that's it. This one was relatively way faster than the other one, right? The other one required a lot of substitution. Okay, let's go over a conceptual problem here. Explain why a single perfectly horizontal rope could never hold up a hanging sign. Use the y component of tension at a horizontal angle. Okay, so you have a hanging sign here. So that means if this is tension 1 sine theta, so we don't have an angle here, but hypothetically, if there was a sine theta, that sine theta would be equal to what? It would have to be equal to the y component, which is mg. Now the thing is, we don't even have a sine theta, right? And it depends on the angle you're looking at from, because I mean, if you're looking at it from this angle, it would be T1 cosine theta, right? Now that would still be this, right? But it's still sine theta, but we don't have a sine theta here. So, because this is a perfectly straight line, there's no components to it. That's why we can't have an mg. If you don't have a vertical component at all, if you only have a horizontal component, the vertical component is 0. That's why the total velocity here, tension total, squared would be equal to tx squared plus ty squared. And ty squared is just 0, so tension total squared is just tx squared, because it's only tx here. There's no vertical component to balance it. Okay? And that's it. There you go. So you have mastered almost all types of force questions that could be thrown at you. But, as caution, I'll be going over the hardest PDF for force questions that you would have probably ever seen. So make sure to check those so you can prepare yourselves for that. Okay? Like I said, my goal is to prepare you for every possible thing that can be thrown at you. And that's what I'm going to do. Make sure to like and subscribe if you like my videos so I can keep posting and reach more people to help.